Hello and welcome. In this video, we're going to look at another example of the current divider equation. In this case here, we have a branch noding right here, and that means that we have a current division. As soon as we hit that node, we know there's something splitting off in two directions. So we have an I1 across the top that's going over this 1 ohm R1 resistor. We have an I2 identified down here, and that's that other half, right? So if we know what I1 is, we can immediately figure out what I2 is using KCL. After that, we see that that I2 current on the bottom is going to split again, and it's going to go some towards the R2, and the other bit of that is going towards the R3. After that, they come back together, right? So we expect the junction leaving here to be I2 current, and I2 current is going to travel up until it reaches this I1 current, and then they're going to sum together to equal the I4 current. And we know that whatever entered the node is also what is leaving the node over here. That means that I4, we immediately know it's got to be 500 milliamps because we can't leave anything behind in the circuit. So let's work on I1. If we want to know the current down I1, then we need to know what this node distributed through, what resistances were being used for that. And we see that they're all in parallel. R1 is in parallel with no resistance down to this node, which means that these two nodes are the same node here. And that gives us R2 in parallel with R3. So our RT is equal to R1 in parallel with R2 in parallel with R3. We'll plug that into our Desmos to solve out for our total resistance here. 1 over 1 over. R1 is 1 ohm plus 1 over 2 ohms for R2 plus 1 over 3 ohms for R3. So we're left with a total resistance. It's pretty small. RT is equal to 0.545 ohms. That makes sense for us because the smallest resistor we have is actually 1 ohm up here. So we knew that this total resistance had to be smaller than 1, and we got that. It's 0.5. So we'll use that to solve for our I1 current. We'll say I1 is equal to our RT on top, 0.545 ohms, divided by the R1 itself, 1 ohm. We'll multiply that by the total incoming current of 500 milliamps, or we can move that back 1, 2, 3 and get that at a amperage value, but we'll leave it at 500 MA. Let's send this out. We're going to calculate that out. 0.545 divided by 1 multiplied by, and I'm going to leave this in milliamps, 500, right? And I know that that answer is also in milliamps. Right, so now we know that I1 is getting 272.5 MA. So we know what the I2 current is immediately. We can say that, well, whatever is not going through R1 has to be going down towards R2. So we'll apply that. We'll say that we'll enter this out and say 272.5 minus our 500 gives us 227.5 milliamps going down towards R2. It's negative just because I flipped those two backwards. We can ignore that because it's not negative, because current can't be negative. So we'll continue on here. Now we know that I2 is going to distribute to these other resistors here. So we can do another current divider equation. We can say, let's solve for I3. And now we no longer have our total resistance, right? Because we actually eliminated a portion of our current. We no longer are dealing with R1 at all. So now we just have R2 and R3 in parallel with each other. And so our total resistance in this case is going to be different than it was before because we've eliminated a portion of our current. So we'll say that we have 1 over 2 in parallel with, so 1 over 3. And that's going to be the total parallel resistance of that bottom portion there, what we have that we're dividing that I2 current through. So we'll say that we have 1.2 ohms divided by what we want to know the current through, which is R3. So we'll put 3 ohms bottom there. We'll multiply by what we have going into that section, which is 227.5 milliamps. So we got 1.2 divided by 3 multiplied by 227.5 milliamps. We know we're going to get milliamps out of that, right? So 91 milliamps. I3 is equal to 91 MA. Now we can find R2 current because we know that we started with 227.5 and lost 91 down the other branch, which means that R2 is going to get 136.5 MA. Right, and this makes sense. If we look back here, we see that the R1, the smallest resistor we have, has the biggest current. The next smallest resistor we have has the next biggest current, and the largest resistor we have has the least amount of current. That's what we expect from our current division. And as we move on, we can double check this. We can say, well, those two currents, 91 and 136.5, should sum back together to equal our 227.5 milliamps. And when we get that back together with our I1 current, we'll see that that is also equal to 500 milliamps. Okay, let us know if you have any questions.